Hello. In the previous video, we studied limits and how to evaluate limits analytically. Today, we study continuity. Let's look at these pictures. So on this picture, suppose that you have some function f of x in here, and this is the graph of that function. Okay, so it's obvious that this function is not defined as c, right? Because there is a hole on the graph. So I hope you still remember the example we consider. Let me copy right here. That is the limit of x cubed minus 1 over x minus 1 when x approaches 1. In this case, c is equal to 1, right? This function is not defined at x equal to 1, but this function has limit at 1. So, when you see something like that, if there is just a hole in here, yes, the function is not defined at this point, but the function has limit. All right, let's move to this example. So our function f of x looks like this. I mean the graph, right? And the function is defined as c. Let's say, as c at this point, that's okay. But of course, in this case, we have a hole. So, from the right, the function is not defined as c. So the graph has two branches, right? Two parts. Of course, in this case, the left limit is different to the right limit. This is the left limit. This is the right limit. You see this? When we study definition of limits, we talk about the left limit and the right limit, right? And the limit exists if the left limit and the right limit are equal. In this case, the function is defined at that point, but the limit does not exist because the left limit and the right limit are not equal, right? All right, so another example is the function has a hole right here, right, on this graph, but you have the function value at that point. So what does it mean? That is the difference with the very first example, right? So you have function x cubed minus 1 over x minus 1. All right, the limit is x, we know, and let's say our function is x cubed minus 1 over x minus 1, right? X is not 1. And I see, yes, there is a hole over there, but I want to make the function like defined, right? Being defined at 1. So I can write as follows. I say f of x equal to x cubed minus 1 over x minus 1 when x is not 1, right? And equal to some number, whatever you want, let's say m, when x equal to 1. You see that? I just want to make an m in here, okay, in this case. So the function is defined at 1, has limit at 1. But, that limit is not right here. You have a hole on the graph, right? You want to fill out the hole. Does that make sense? But if you have m right here, so that is different to this guy. So you cannot fill the hole. The graph still has the hole over there. Does that make sense? All right, so what we are talking about right here, we are talking about discontinuity, right? All these three examples are discontinuous. Three graphs are discontinuous because, there is a hole in the first graph. There is a very big gap in the second graph. This is the gap right here, right? Very big. And this is also a big gap right here, right? So these three graphs are discontinuous. So what is continuity? A function is continuous at some point if each graph is continuous, right? Means looks like continuous. There is not any gap, there is not any hole on the graph at that point. Okay, so this should look like this. So if you have C right here and you want to consider continuity, right? Continuity of the function f of x at that point. So you can see Actually, the function should be defined at that point. Is it correct? That means, the function value fc is defined. Secondly, the limit should as x, right? And not only as x should equal to the function value. So you just cannot, here the limit as x, you see? In this case, the limit as x, right? But that is not the function value. The function value is right here, you see? So these two values are different. That's why the function is still not continuous. So in order to have a continuous function, we need two conditions. The first one, fc is defined. That means, in another word, we can say c is in the domain of the function. Of f of x. Secondly, the limit as x and equal to the function value. All right. So in this video, we study how to test a function to be continuous, and then we will consider this type of functions. We need to find m such that the function is continuous. Make sense? That means, like here, you have a hole, right? You have a hole right here, and you want to fill out the hole, as I just mentioned previously, and we want to make that function continuous. And of course, the limit will play the key role in continuity. You see, there's no way to avoid limit. Sorry, right here. So we need to consider limits, okay? Let's consider the following example. F of x equal to 1 over x. So we know that this function does not have limit at 0, right? Let's say the domain of this function is the whole number line except 0, okay? And we know that the limit of this function at 0 does not exist. Other than that, if you plug any point, non-zero point, right, into the function, you get a finite number. You are good, right? So we can do conclusion. This function, 1 over x, is continuous everywhere except x equal to 0. That's it. We'll go back to this example later, okay? But let's consider another one. Let's say x squared minus 1 over x minus 1. Again, the domain of this function is everywhere, right? The whole number line except one point, x equal to 1, right? Because x minus 1 is not 0, okay? And we know that the limit of this function is x. So this is very similar to the case x cubed minus 1 over x minus 1. But let's solve this, right? So I have x squared minus 1, x minus 1, x approaches 1. I plug 1 into the function. I got 0 over 0, right? And that means I need to factor this. I get, x minus 1 over x minus 1, x approaches 1. So I need to find another factor. So here I should have x. The free coefficient is -1. That means I have -1 in here. No plus 1, because plus 1 with negative will be negative. Okay. Then I simplify x minus 1 with x minus 1. I got limit of x plus 1. X goes to 1. So that is 1 plus 1, which is 2. Perfect. The limit is x, but the function is not defined at 1. So we can do conclusion. F of x is not continuous at x equal to 1. All right. But from here, if I create a new function, g of x equal to x squared minus 1, x minus 1, when x is not 1, and 2 when x equal to 1. So see what happened. We see that x equal to 1 is in the domain, right? And g of 1 is equal to 2 because of this. You see that? And the second condition, the limit of the function g of x when x approaches 1 is equal to 2. We just saw that right here. And this is the function value. From here, by the definition of continuity, the function gx is continuous at x equal to 1. You see? So that's how we can test a function is continuous or not at some point. But look at this. If you compare this example and this example, 1 over x right here and x squared minus 1 over x minus 1. You see? For 1 over x, there is no way to add 0 to this function. There's no way. Why? Because if you remember, the graph of this function looks like this. Like this. The left limit is negative infinity and the right limit at 0 is positive infinity. I hope you still remember that. But it's easy to imagine, right? And since there is a big gap in here, right? There's no way to fill the gap. Does that make sense? And in such situation, the point x equal to 0 is called the point of discontinuity. And let's say unremovable. Unremovable discontinuity. That means you cannot, remove this discontinuity. You cannot make this function become continuous at this point. Does that make sense? This is about, the very first example right here. So for this, you have a big gap in here. There's no way to fill the gap. So this function is discontinuous and the discontinuity is unremovable. I write here. Unremovable. Removable, right? Sometimes they say, yeah, that is discontinuity of the first time or of the second type. But, let's say unremovable in this case. All right, so what happened in the second example? We see that the second function is not continuous at 1 because 1 is not in the domain, right? Given that the function has limit. And then we see that, yeah, the function has limit and equal to a finite number. So I just add that point, right? I just add that limit to the function. That means I make the function being continuous by adding 1 point, by filling the hole on the graph. So in that situation, x equal to 2. No, x equal to 1, the point 1, right? The point 1 right here. Let me write here, the point 1. Again, this is discontinuity, right? Continuity. But this is removable. That means you may add the point, right, to the graph and make the function continuous. Okay, don't forget that. I'll tell you a very interesting thing, right? So if a function is continuous, that is okay. But, we are more interested in discontinuity. That is the thing, okay? Because, there are a lot of informations at those points. Like this. Unremovable and like this. Removable. So let's consider properties of continuity. If you have B is a real number, f and g are continuous functions at some point C, then the following functions are also continuous at x equal to c. So this scalar product, somewhat difference, the product of two functions and even the quotient if we have this condition, g of c is not 0. So, that is very natural, right? It's very natural and then very easy to understand. It comes from, properties of limits. I hope you still remember that. The limit of this guy is just equal to b times limit of f. The limit of this guy equal to sum or difference of limits. Limits of product is product of two limits, and limit of quotient is equal to quotient of limits in case if the limit of that point in here in the denominator is not 0. So, it's okay. It's not surprising at all, right? And from here, we also have another property for composite function. Okay, so if you have some function f and you need to evaluate, f of g of x, let's say that is h of x, and we know that the function g of x is continuous at c. The function f is continuous at g of c. Then from here you can see that the function h of x is continuous at x equal to c. That's it. It's very natural, right? In order to finish today's lecture, we consider two functions, fx equal to tangent of x and fx equal to x sine 1 over x when x is 0 and equal to 0 when x is equal to 0. So this is piecewise function, okay? And this is trig function tangent. We need to describe the intervals on which each function is continuous, okay? So we know tangent is sine over cosine. Then for such function, we need to find Rx, where the function is not continuous. So they ask us to find the interval on which the function is continuous, and we will find the interval, or we find all points where the function is not continuous, right? Or discontinuous, okay? Or discontinuous. And then we just take the other part, right, from the number line. That's it. All right, so I will show you two ways to do this, okay? So the first way, we see, yes, tangent is sine over cosine, so the function is defined everywhere except x, where cosine of x equal to 0. So we need to solve the equation cosine of x equal to 0, right? And we exclude all those points from our consideration. And then we'll get intervals on which the function is continuous. The unit circle, we discussed about that before, right? Because, trig functions are really good on the unit circle. So the cosine axis is this guy, right? Is the horizontal. Okay, so cosine equal to 0. Where's that? 0 is right here. This is 1. This is -1. This is 0. In order to find Rx where cosine equal to 0, so you need to draw the vertical line, right, at 0, because we are discussing about 0. If you get any number right here, so you can make, vertical line like that. Makes sense? But we are discussing the function at 0. So at 0, I have vertical line, and this vertical line intersect with the unit circle at 2 points. This point is corresponding to pi over 2, and this point is corresponding to 3 pi over 2. Or if you want, you can write negative pi over 2. They are the same. They share the same position on the unit circle, right? So cosine equal to 0 only at this point. I write x equal to pi over 2, right? Okay, look at this. How to write general solution. If you are at pi over 2, you move 1 pi, you get 3 pi over 2. and you move one more pi, you get back to pi over 2. That means if you move by k pi, you get cosine equal to 0 because you will be on one of these positions. Does that make sense? So I write here pi over 2 plus k pi, where k is what? Is 0, 1, or let's say plus minus 1, plus minus 2, and so on. Because you have negative, because we have this. We can go in the negative direction. Make sense? Okay, let's repeat again, right? This direction is positive, but if you go in this direction, you get a negative direction. Okay, all right. So if you exclude everything from this, you get the following. You have the first interval, or you can write a solution. Okay, let me write solution in here. The whole number line except those points, pi over 2 plus k pi. And where k is equal to 0, plus minus 1, plus minus 2, and so on. Right? If they want, you can write intervals like this. This is equivalent to, first is from negative 2, pi over 2 to pi over 2. That is the first interval right here. Right? And then the second interval right here. So I just move to the next interval. I write union with what? With pi over 2 to 3 pi over 2, right? And then union with 3 pi over 2 to, you add one more pi, you get 5 pi over 2, right? And so on. This is in the positive direction. If you move to a negative direction, so you get negative pi over 2 from negative 3 pi over 2 to negative pi over 2. So you subtract 1 pi, okay? Subtract 1 pi, or you add negative 1 pi. In this direction, you add pi, okay, each time. You see these two endpoints, so they are different in 1 pi, and so on. You know, that's how we can write the solution. So in this way, or in this way. Okay, this is about cosine, because we know tangent is sine over cosine, but we also know about tangent without sine cosine. I mean, on the unit circle, let me remind you that. So you have, you know, unit circle right here. This is cosine, this is sine axis. Where's the tangent? Tangent axis is here. That is the tangent axis, right? So you might think, yeah, the tangent is not defined where? Oh, by the way, how to find the tangent of x? If you have 0 and this is the angle x, in order to find the tangent value, you just, you know, connect this point with the origin, and that straight line will intersect with the tangent axis at some point. That is the tangent of x. Okay, so you might think like you move this point right around the unit circle in here. Everywhere, almost everywhere, you can determine tangent, but except 2 points, this point, this point. There's no way, right? If you connect this, the origin, with 2 points right here, so this straight line is parallel to this straight line. Since they are parallel, they will not intersect with each other. Make sense? That means, you know, tangent is not defined at this point and at this point. That's it. So you do almost the same thing, write out the interval. Does that make sense? So, you know, unit circle is really good for this. All right, let's move to the next example. For this function, you have x sine 1 over x when x is not 0, and the function is 0 when x equal to 0. If you look at this, you might think, yeah, the function is not continuous at 0. Of course, because, you know, in this case, right, if you only look at this, the function is not defined at 0 because you have 1 over x in here. There's no way to divide by 0. But in this case, they already at 0. You see, they already define the function value as 0. So this is f of 0. Okay, and we need to determine if the function is continuous as 0 or not. Okay, So we need to test two conditions. The first one, 0 is in the domain. Of course, we already see this right here. Okay. The second condition, limit of the function as x at 0 and equal to the function value means equal to 0 right here. Right? So we need to check this condition only. Okay. So let's consider the limit of this guy. Right, limit of x psi of 1 over x when x approaches 0. If you separate psi of 1 over x and x, right? The limit of x at 0 is 0. But the limit of this guy at 0 does not exist. So there's no way to apply the product, right, rule. Like limit of product equal to product of limits. Since this is undefined, or say the limit does not exist, right, at 0, so you may not multiply 0 with that to get 0. Okay, that is not 0. We need another approach. We need to use the squeeze theorem. Right? We need to use the squeeze theorem. Let me tell you the reason, right? We know that sine of 1 over x is in between 1 and -1. I don't care about this number, right? But I know exactly the function value of psi is in between -1 and 1. That's it. And when you multiply with the x, right? When you multiply both sides with the x in here, right? So you might think like, yes, in one bound, upper bound, okay, let's say, we have to be careful at this, right? But let's say x greater than or equal to 0. And I multiply with the x, I get x psi of 1 over x less than x and greater than -x. You see that? And we consider the limit at 0. The limit of -x and x at 0 are 0. So if we apply the squeeze theorem, you get what you need in here. The limit of this guy should be 0. Makes sense? I write here the function equal to the limit of x when x approaches 0, x approaches 0, x approaches 0, and all this equal to 0. What is this? 0? 0 is the function value. So that means the function is continuous. I will write a detailed solution. That is just some analyze, okay? Some analysis about the function, because we have x psi of 1 over x, and we know that if your function is bounded right here, you multiply both sides by x. Yes, maybe you have bounded function as 0, and that's what you get. But when you write a solution, you have to be very careful in this situation. Okay, so because you cannot just divide 3 sides, let's say 3 sides by x, because we don't know x is positive or negative. If x is negative, so when you multiply by a negative number, your inequalities will be reversed. Don't forget that. That's why I add the condition x greater than or equal to 0. Okay? But I know exactly the following one. I can avoid this. I can write in the following. I have -1 less than or equal to psi of 1 over x less than or equal to 1, right? From here, I get x psi of 1 over x less than or equal to absolute of x and greater than or equal to negative absolute of x. That is for sure. That is true. Okay? So, from here, you have the limit of negative absolute of x less than or equal to the limit of x psi of 1 over x less than or equal to the limit of absolute of x when x approaches 0. this is 0, this is 0. So from here, you get 0 right here by the squeeze theorem. All right? So this function is defined at 0. And this condition is satisfied. That means the function is continuous at 0. And of course, the function is defined everywhere else. So from here, I can write f of x is continuous on the whole number line. Okay, this is continuous. So I hope that the video is clear enough. But if you have any questions, please feel free to let me know.